One final example of a Taylor series is we're going to find the first four terms of the e to the x Taylor series centered about the point ln of 3. So n, we're going to have 0, 1, 2, and 3 at least. Then we're going to have the nth derivative, right? And the good news is the derivative of e to the x is always going to be e to the x. All right, so this one's really nice. And then finally, when we substitute ln of 3 back in, the nth derivative at ln3, e ln 3 is going to be 3. And that's going to be for all of these. All right, so that makes it really easy for us because we don't even need to find a pattern for this. All right, so for the first three terms in our Taylor series here, all right, so we're going to have that we have 3. Okay, so this is, I think, the first time that we've actually had the 0th term actually work, okay, or becomes a non-zero term, plus 3x minus ln of 3 to the first, plus 3 over 2 factorial x minus ln of 3 squared, and then finally plus 3 over 3 factorial x minus ln of 3 to the third power. Okay, so, and of course we could factor the 3 out if we really wanted to, and we could just rewrite this. But again, this is the first 4 terms. All right, so this is term 1, 2, 3, 4, the first 4 non-zero terms. Now for part B, we could factor that 3 out, and we could write this as 1 plus x minus ln of 3 to the first, plus, I'll just say x minus ln of 3 squared over 2 factorial, plus x minus ln of 3 cubed over 3 factorial. All right, and of course, because we're looking for the summation notation, this is just going to go on infinitesimally, right? And so if we look at this realistically in the denominator, okay, we just have, like, this would be 0 factorial and this would be 1 factorial. And so it looks like that the best way that we could write this is we could factor the 3 on the outside. We would have n equals 0 to infinity. And then we would have x minus ln of 3 to the nth power divided by n factorial. All right, and again, that's because we always have an x minus ln of 3. This 3 is on the outside of the series. And then in the denominator, notice that it always matches up to the power of whatever our exponent is. All right, so that's going to be our Taylor series for this one. All right, so that one's not so bad when you're dealing with the e powers. All right, so what's the purpose of all this mess? Well, one thing that we've seen in previous videos is that we were able to approximate values of not so nice sort of values for this and approximate. And that's what we're going to do. We're going to use our Taylor series centered at 0 to be able to maybe find the first 4 non-zero terms. And then we're going to use those terms to approximate 1.09. All right, now for us, we just have to remember that 1 plus x has to be equal to 1.09. And so what that means is that when we substitute back in for x, we're going to use 0.09. Okay, so keep that in mind. And since it's centered at 0, a is going to be equal to 0. So in reality, it's just a Maclaurin series. Okay, so let's get to it. Okay, so we're going to have our nth derivatives. Okay, so we have 0, 1, 2, and 3. We're going to write this as 1 plus x to the 1/5 to start. All right, and that's just the 0th derivative. And remember, this is the nth derivative. So this is going to be f sub n, or f nth derivative of x. Right? Then we're going to find fn at 0. We're going to see if that simplifies that. All right, so next one is going to be 1/5, 1 plus x to the minus 4/5. And then the next one is going to be negative 4/25, 1 plus x to the minus 9/5. And then finally, This is going to turn into 36 over 125, 1 plus x to the minus 14/5. All right, now that looks ugly, but there is some good news. Remember, we're substituting 0 back in for each of those x's, right? At least initially, right? Because we want to find fn at 0 for the derivatives. So when we do that, that's going to be 1 plus 0 to the 1/5, which is just 1, right? And then we have 1/5 of 1 plus 0 to the minus 4/5, and that's going to be 1/5. And it just seems like each time as we're substituting values back in, all right, we just keep getting 1 for this animal. And so we get negative 4 over 25. And then finally, this is just going to be 36 over 125. But when we substitute 0 back in, that just becomes a 1. All right, so for our Taylor polynomial centered at 0, this is going to be that we have 1 plus 1/5 x. Now, technically, it's x minus 0 because it's centered about 0, but we'll just use x. Right? Don't forget that the next one has to be divided by 2. So this is 4 over 25 divided by 2 factorial x squared. Right? And then finally, plus 36 over 125 divided by 3 factorial x cubed. All right. And so if we simplify this just a little bit, our first 4 non-zero terms, 1 plus 1/5 x minus 2/25 x squared plus 6 over 125 x cubed. All right. So those are going to be our first 4 non-zero terms. At this point, we're going to go through and we're just going to substitute 0.09 back in. Okay, and that should be able to approximate the 5th root of 1.09. And then we can use a calculator to see how close or how far off we were. This is going to be 1 plus 1/5 times 0.09 minus 2 over 25 times 0.09 squared plus 6 over 125 times 0.09 cubed. All right, now to be able to do this, I'm going to go ahead and I'm going to use Desmos calculator. So Desmos scientific calculator makes it a little bit easier. So credit to Desmos. So we're going to have 1 plus, and it was 1/5 times 0.09, and then minus, we had 2 over 25 times 0.09 squared. Right, and then finally we had, I believe it was 6 over 125. Let me just verify that. Yep, 6 over 125. That's not 115. That should say 125. Sorry, writing on the screen's always not much fun. All right, and 6 over 125 times 0.09 cubed. All right, so when we execute that, that's 1.01738. Okay, so that's going to be the series approximation. So 1.017386992. All right, so that's what Desmos gives us. Now let's go ahead and see what the actual answer is. So if I took 1.09, and let me clear that out, sorry. So I'm going to do the nth root, 5th root of 1.09. Let's see how close it gets us to it. Pretty darn close. Okay, so it looks like it's good to the tenths, hundredths, thousandths, 10,000ths, 100,000ths place. So that's pretty accurate using our 3rd degree Taylor polynomial. Okay, all right, so that's everything for this section. Okay, and we've now seen that Taylor and Maclaurin polynomials and also Taylor and Maclaurin series, how to try to write them. Okay, so finally in the next section, we're going to start doing some calculus applications with series.